Today I'm going to discuss a little bit on NVIDIA's CUDA C++ programming in Windows. I have here Visual Studio 2019 and my desktop PC that I'm using here has an NVIDIA GeForce 1050 Ti. It's an old video card but more than enough to do CUDA programming. In order to integrate CUDA programming in Visual Studio, once you have Visual Studio, you first need to go to the developer.nvidia.com, download the CUDA Toolkit installer, install it, and follow the instructions of the installer dialog. It shall find its way as a project template when you start a Visual Studio project. There will be a project template uh, called CUDA runtime. Select that template and it will generate example project that we are looking here. So I'm not the one who write the source code here. This is pre-generated by the template. So we can see here that we have the kernel.cu. This is the only source code that we have. The CU extension is important as it is to indicate that this source code is a CUDA source code, meaning it has an extended form of C++. We will go right now what I mean by extended. This line 93 here is what that extended instruction looks like. As an extended instruction, this line 93 will not compile in a C or C++ in any standard C++ compiler. You can see below here that when I build this project, it is in fact using a different compiler. It is using the nvcc.exe compiler from NVIDIA. So again, this will not compile using a Microsoft Visual Studio compiler, or if you're in Linux, it will not be honored using the GCC compiler. Only the compiler from NVIDIA can understand this line 93 here. Now let me explain how the CUDA programming is all about. So you will recognize that this generated source code here in fact is 99% looks like a C code. It has your entry point main, and all the statements here are in fact valid C code. And in fact, only line 93 looks like the one that is invalid. The rest are all understandable as something that is you might consider C, C++. Okay, the odd kernel is defined here, and you will notice that there's a global decorator. Again, you can easily simulate this in C++, but in the context of CUDA, it has its own specific meaning. And the function also has its standard C-looking function parameters. However, there is the presence of this thread IDX, a variable that is nowhere to be found in the source code. You can also see here that I declared a class Smeagol, and we are able to compile. Therefore, the NVCC indeed understands C++. Now, the question here that you should ask yourself is, why is it called a kernel? What is a kernel? Before the CUDA programming, you have a for loop that iterates through a million times, and at the heart of this nested for loop is this instruction here, which is trying to add the elements of the array. C equals A plus B at the I index. So imagine a nested for loop sequentially processing each of the elements and performing this operation. So if the array is a million, then each of these will be sequentially performed. That heart of the for loop, which is this one, is the kernel. In the CUDA paradigm, you are to extract that heart of the for loop and transfer that to a kernel function. The CUDA dispatcher will be the one to generate an I index. So this function here will be executed by different CUDA cores or processors. Thousands of them, each with a different I. So we can begin to see now that instead of doing a for loop in the CUDA paradigm, this block here will be simultaneously executed through a different hardware processors simultaneously. This means that the logic of that nested for loop has an implication that each of these addition of the array here is independent of the other array, meaning that the program is inherently parallelizable. If it is not parallelizable, then CUDA could not help you. Therefore, you could not just take a C++ program, compile it with NVIDIA CUDA, and expect it to speed up. Cannot be. You have a homework and an enormous task to redesign the program to identify the parts that can be parallelized, extract the kernel of this parallelizable code, and express it as a kernel block here. Not an easy task. Example, the chess engine Stockfish has been attempted to be parallelized through CUDA, but since no parts of the code logic in the chess engine is parallelizable, therefore it could not be parallelized. So therefore, there are classifications of programs that are parallelizable, mostly those that access a huge number of array matrix multiplication, but there are also classes of programs that cannot be parallelized. If we go to the main, we can see CUDA here, you can see CUDA malloc, because the CUDA processor has its own memory. Whatever is the output of the CUDA cores is written into its own memory. And once it's completed writing to its memory, we have to copy that memory back to the CPU memory or RAM. Take note of this direction here. CUDA memcpy host to device. Host is referring to the CPU, device is referring to the GPU. So this is to indicate that we are going to transfer the memory from RAM to the memory of the GPU. If you go to the line 86 here, you will notice that here in line 111, you will notice that the direction has been inverted. It is now device to host. So the output of the CUDA, which is the device, is now copied to the host, after which you can now print the result. You can access the CPU, can now access the result and print it as or continue processing as what is needed. So this is the principle of NVIDIA CUDA programming. Two processing units, each with their own memory, and you are to copy memories back and forth, and then you are going also to free it, invoke a kernel, and you are not responsible how many I mean it is the CUDA that parallelize the execution of the add kernel in parallel. You just have to express it like this, and they will be parallelized. In actual practice, the sections of code having this CUDA extension like the kernel is to be separated into its own CU, that CU extension source file, compiled through with NVCC compiler, generating an object file. This will allow the rest of the code in the program to be written in pure C, C++, and together the object file from NVCC is combined into the application at link time. So this will make the application more portable and more manageable, as majority of the code base, 99.9%, appears as a C, C++, whereas the CUDA portions are separately segregated into its own CU file with a different compiler and link joined during link time. So in platforms that have no CUDA, you can opt to have a alternative implementation of sequentially doing it in a CPU. So you can use a preprocessor in your program because you have separated the CUDA portions. I have seen this done in the dlib face recognition library, and I believe this is the best practice in the CUDA programming out there. This is a template, so we are looking at a mixed C++ CUDA here, but I'm just describing how it should be done in real practice to have a more portable program. Thank you.